Right. Hello, everyone. Uh, I guess the times have changed. So the timing of this session was changed and it was preponed because of some emergency. So I guess you have been informed. The mail was sent that the Saturday session will be conducted from 11 a.m. to 1 p.m. It's already 11:17. All right, we'll wait for another 2 to 3 minutes. If nobody else joins, we'll start the session. I see only Manisha has joined. Hi, Manisha. I have allowed your mic. Can you unmute yourself and speak? Can you see my screen? Oh, Manisha, you're on hold. Hi, Shashi Kumar.
Good morning, sir.
Good morning. Can you see my screen?
Yes, sir, it is visible.
And can you also confirm if whenever I'm changing the slides, it is changing as well?
It is changing clearly.
Okay. Okay, thank you. Okay, let's start the session.
Okay, sir.
Yeah. Okay, hello everyone. Welcome to the weekly discussion and doubt clearing session of session number 6 of the NPTEL course Maintenance and Repair of Concrete Structures NOC 23-CE06, which is taken by Professor Radhakrishna G. Pillai of IIT Madras. I am Ashirvad Satpathy. I am a PMRF research scholar at IIT Delhi, and I am the officially assigned teaching assistant for this NPTEL course. What I do is I usually take this weekly discussion and outlining sessions where we discuss the previously given assignment questions and how to approach them, how to answer them, and we also take some of the doubts that you might be having related to the previous week's lectures, and we discuss those doubts and these assignment problems. So basically, there is another teaching assistant to this course. His name is Umesh. He usually takes his weekly sessions on Fridays from 7 to 9 p.m. And I take my weekly sessions on Saturdays from 6 to 8 p.m. usually. But for today, due to some emergency, we have preponed this session to 11 a.m. So this session will be going on from 11 to till 1 p.m. today, for today only, and the rest of the sessions will be, every time you'll be provided with, you'll be sent a mail regarding with the link of the session and with the date and timing of the session as well. So before moving on to start today's session, I also want to mention that I record these weekly discussion and outlining sessions, and I post these videos on YouTube. So I have shared the link of the YouTube video of the last week's session in the meeting chat. You can go and check it out if you have missed the live session. Also, I save these slides that I use for this session, and I upload it on a OneDrive folder, and I've shared the link of that folder. So the link of that folder remains same for the due course of this NPTEL subject, and I'll be keeping on uploading the slides, the lecture slides uh, on in that OneDrive folder. All right. In today's session, we'll be discussing the week 5 assignment 5 problems. There are around 8 problems that were given to you, and the week 5 lectures were more or less related to the repair strategies and different repair technique. The assessment techniques. Like, let's say, half cell potential techniques or surface resistivity techniques to assess the corrosion resistance or the state or the condition of the corrosion of the reinforcement in actual structures, and what are the type of strategies and what are the properties of the repair materials that you're going to choose in order to carry out a repair and maintenance work in an already existing reinforced concrete structure. So we'll be discussing the assignment problems of the week 5, and at the end of the session we'll be also taking some of your doubts you might be having regarding the week 5 lectures, which was related to the repair and maintenance of the concrete structures. All right. The first question was, why do you think the corrosion condition assessment of a pre-stressed concrete system is more challenging than a reinforced concrete system? The options given were: due to the typical larger concrete cover depths in PSC systems than RC systems, due to the unnoticed localized pitting corrosion in the pre-stressed strands, due to the interstitial space between the 7 wires of strands and hence late oozing out of corrosion products through cover concrete and the development of cracks, due to the high strength concrete used. Which of these options are correct, and why do you choose those options? Please unmute yourself and speak. You can raise your hands. I have allowed your mic since there are only 2 participants. I've allowed both of your mics. You can raise your hands or you can choose to unmute yourself and answer this question. Let's keep this session interactive. Yes, anyone of you would like to answer to this question? Manisha, Shashikumar? I've allowed your mics. You can unmute yourself if you and you can speak if you want.
It is due to unnoticed localized pitting corrosion in the pre-stressed stanza,
Okay.
and it may be the another reason due to the interstitial space between the 7 wire of stanza.
Okay, you're saying that these two options are correct. And would you please share some details regarding this option? Like, why do you think there is a unnoticed localized pitting corrosion? Or what is the difference between, I mean, why the presence of an interstitial space would affect the pre-stressed concrete systems? Can you shed some light on that?
Is
Okay. Okay. Thank
okay.
you, Sashi Kumar. Yes,
Thanks,
you
thanks.
can mute yourself. Yeah. Okay. The correct answers actually are three of these options. The first is that due to the typically larger concrete cover depths in PSC systems than RC systems. The second one is the due to the unnoticed localized pitting corrosion, and the third one is the due to the presence of the interstitial space between the 7 wires. And the third option, the fourth option is typically not related to the corrosion I mean the difficulty in the corrosion condition assessment because um, so presence of a high strength concrete would in fact um, when corrosion is occurring on the pre-stressed strands of steel inside the pre-stressed concrete system. So when the corrosion products are deposited on these strands, there will be an expansive stress caused between the concrete. And if the concrete that is present, which is of a high strength concrete, it'll there will be in fact a larger stress inside the concrete, and that won't cause any problem in assessing the corrosion condition of the PSC system. Rather, these three options would cause, and I'll discuss each of these statements one by one. The first one is due to the typical larger concrete cover depths in PSC systems than RC systems. This is true because typically in RCs, in PSC systems, the concept of cover is different from that of RC systems. We choose the position of the steel reinforcement of the or the pre-stressing reinforcement strands based on the loading pattern that is going to occur throughout the span of the beams or let's say any other elements. So therefore, the concrete cover depths that is present in pre-stressed concrete systems is quite large as compared to that of reinforced concrete systems, and therefore, whenever there is a crack that is occurring inside the concrete due to the corrosion, for it to propagate to the surface of the concrete system, that will take more time in case of pre-stressed concrete system than that in case of reinforced concrete system, because since the pre-stressed concrete systems have a larger cover depth, so the crack might initiate, but for it will take more time than reinforced concrete systems to reach to the cover, to appear on the cover, or to appear on the surface. The crack to appear on the surface, it will take more time. Therefore, this causes a problematic situation to assess the condition, even if there is a corrosion occurring and hence a crack has already been created inside the concrete, but it will not appear on the surface for a long period of time, and that will cause a kind of a explosive spalling condition in case of pre-stressed concrete systems. So it is a very dangerous condition due to that. The second statement was due to the unnoticed localized pitting corrosion in pre-stressed strands. And that is true because, again, these pre-stressed strands are arranged in this kind of a pattern, as you might have also seen. So this I'm showing uh, the cross section of the pre-stressing strands. So typically what happens is there might be localized pitting corrosion on the pre-stressing strands because whenever there is a chloride attack, sometimes what happens is you have to grout these ducts. So this is the duct, and these are the strands. So after uh, pre-stressing the strands, you have to grout the inside of the duct with a suitable concrete or a concrete grout. And sometimes what happens is, you might have also seen this in the lectures as well, due to the curvature of the strands inside the beam. Let's say this is the beam, and this is how the strand is moving. Whenever you're grouting, um, the upper surface, let's say this portion which is at a lower depth, that will be properly grouted, but at upper surfaces the only the lower portion will be grouted, while the upper portions will be remaining vacant. This will create this will allow for moisture and other elements to to get inside the concrete and affect the reinforce the steel strands, and that will cause corrosion to happen. And sometimes if the chloride induced corrosion can occur on these pre-stressing strands, then that will cause a localized pitting corrosion. And it is difficult to detect the localized pitting of these strands because it might start to corrode inside. The strands might start to corrode, but it will not appear on the concrete surface as soon as it appears on a reinforced concrete element, because reinforced concrete elements have a lesser cover depth and they're directly exposed to the concrete, the substrate concrete. But in case of pre-stressing strands, it is within a duct which is inside the concrete element. So there will be no signs of corrosion, like there will be no rust stains on the concrete surface, and therefore it is difficult to detect corrosion in case of pre-stressing elements. And the third statement was, due to the interstitial space between the seven wires of the stands and hence late oozing out of corrosion products through the cover concrete and development of cracks. So what happens is, in case of these pre-stressing strands, whenever one of these strands or several of these strands start to corrode, the initial corrosion products start to accumulate at these locations inside the interstitial spaces between the strands. So these are the gaps which might not be filled with grouts, sometimes due to improper compaction or improper grouting techniques. These might not be filled with grouts, and therefore these corrosion products start to accumulate at these locations, the interstitial spaces. And therefore the corrosion is ongoing, but it is not visible, or there is no expansive stress caused by this accumulation of the corrosion products, because they're accumulating in a gap that is already present. So they're not putting any expansive stresses on the concrete, but the steel is getting corroded, and hence it is losing the structural capacity, the capacity to take loads, and that will cause a severe, a devastative failure if the steel has corroded sufficiently. There's a localized pitting corrosion. There is not enough cross section of the steel available for it to take the applied loads from the structure. Then it will cause a devastative failure due to the applied loads as well as due to the corrosion. So these are the three options that are correct. Due to these three problems, generally the assessment of corrosion, the condition of the corrosion or the degree of corrosion in the pre-stressing pre-stressed elements is difficult or more challenging than that in a reinforced concrete elements. All right. Moving on to the second question. Specifications or limits on the half cell potential in ASTM C876 standard for probability of corrosion is not valid for all types of steel when embedded in concrete. However, the observed half cell potential values and contour plots can be used to assess the relative probability of corrosion. Is it a true or a false statement? Can somebody answer to this question?
Sir, it is true only, sir.
Okay, and why would you say that?
Because this offshore potential test will give the probability of corrosion. It will not give the rate of corrosion.
Okay, okay, and what is the difference between the probability of corrosion and the rate of corrosion that you're talking about?
Probability means it is the chance, sir. Whether it is corrosion is initiated or not, like that only we can find out.
Okay, okay, and
But rate,
rate of
rate
corrosion
means,
is?
yes, sir.
Rate of corrosion is?
Rate of corrosion means what is how much it is happened, how progress we cannot monitor.
Okay,
That's,
okay, okay. Thank you.
thank you.
Thank you, Sashi Kumar. Yes. Thank you for answering this question. Yes, it's a true statement actually. The specifications or limits on the half cell potential that is given in the ASTM C876 standard. So there are, the limits like they say that if the measured voltage is less than minus 0.35 volt or minus 350 millivolts, then there is 90% chance of corrosion. And if the measured voltage is greater than minus 0.25 volt or 250, minus 250 millivolts, then there is 90% chance of no corrosion. And this is from the ASTM C876 standard of half cell potential values. And this has been also discussed in the lecture as well. These values tend to work, and these values are applicable to a lot of law. So as we know that the corrosion of steel reinforcement is not just dependent on the steel itself, it is also dependent on the substrate concrete, the concrete, the type of concrete, the materials that are used, the porosity, the permeability of the concrete, and the how is the what is the how is the microstructural development, and what are the degree of hydration of the concrete. All these elements also affect the corrosion of the steel reinforcement embedded within the concrete. Now we know that these half cell potential values, these are the half cell potential test is an effective test to assess the corrosion potential or the probability inside inside the concrete. However, it is not applicable to all types of concretes or all types of steel reinforcement. We have also seen that in the lecture as well, like different concretes with added with various supplementary cementitious materials or SCMs like fly ash or let's say the use of blended cements, which have a very highly refined microstructure like the limestone calcine clay cement LC3, or let's say in case of pozzolana, Portland pozzolana cement as well, if they have a very compact microstructure and the permeability is very low, and it has a very high resistivity, then the half cell potential values will lead to misleading results. Like there might be corrosion happening, there's a sufficient chance of corrosion, there might be corrosion happening, but the half cell potential values will show you very high potential values, which will so going by this definition, it will show you that there is no corrosion occurring, but it might. So these are misleading information in case of certain type of concretes or certain types of steel. What you can do with this half cell potential values? Yes, you can draw these contour plots that they are talking about. So typically in a half cell potential test, what they do is, so let's say uh, this is a concrete column, and these are the reinforcements going inside the concrete column, right? What they do is they chip off the cover concrete, and they place a connection, so one of the electrodes is attached to the exposed reinforcement, and one of the electrodes contains a reference electrode. This is the reference electrode. This is typically saturated CuSO4 or copper sulfate solution. So this is the reference electrode, and it has a sponge. So the reference electrode looks somewhat like this on the concrete surface. This is the surface, and it has a sponge, and this is the concrete surface. So this is the sponge, and this is the reference electrode. So one of the electrodes is attached to the exposed steel reinforcement, while the other reference electrode is moved across the concrete surface, and the measurements are taken at different locations. So you can draw a grid. Let's say this is a concrete element. So what you can do is you can draw a grid, and you can take the measurements as all these locations, and based on the values, you can draw a plot. So drawing a plot, as in you can draw from the depending on the depth, so depth from top, and the measured potential values, and you can based on the degree of the amount, the potential values, and that you can draw a contour plot. Like, let's say this portion of the concrete has a this portion of the concrete has less potential values, this has higher potential values. So you can draw contour plots and do color grading of these contour plots to give you an indication of what is the potential of the corrosion inside the on the concrete surface. So based on the as you move on over the concrete surface, what are the potential locations of the corrosion, and this can give you a relative probability of corrosion, not the exact absolute value of corrosion or the absolute value of the probability of corrosion. Rather this will give you a relative probability. Let's say this location has corroded a lot, so it'll give you a higher potential values compared to these locations, or compared to another concrete element. This concrete element can give you higher potential values, as in higher negative potential values, and that will give you an indication that this location or this particular element has a higher probability of corrosion, and hence this particular location needs to be repaired suitably, and so therefore you can carry out the repair work. So you can't assess the absolute degree of corrosion, at which state of the corrosion, at which state is the corrosion occurring, like is it in the initiation phase, has the corrosion already propagated, or is it before the initiation phase, or the corrosion is just starting, or it is already corroded and there is a significant loss of the cross section of the steel. So you can't assess the absolute degree of corrosion inside the concrete reinforcement using this technique. However, you can have a relative idea of what is the degree of corrosion or what is the potential of the corrosion at certain location on the concrete surface. So this is a true statement, and these kind of techniques like the ASTM C876 for the half cell potential, or we'll be discussing about the ASTM G109 method or the Rylium TC 154 method that was also discussed about in the lecture. This will give you just a rough idea or a relative idea or of the kind of corrosion or the degree of corrosion that is, or the potential of the corrosion that is going to occur inside the concrete. However, they won't give you certain absolute values of or the degree absolute degree of corrosion, at which state of the corrosion, at which state is the steel corroded. They won't give you that. All right. Moving on to the third question, the ASTM G109 test that we just talked about. The ASTM G109 test method assesses macrocell corrosion between multiple rebars, and hence it is not valid for corrosion assessment of steel in highly resistive concrete systems. This is because in such systems, the macrocell and microcell forms between the surfaces of the same steel rebar. Is this a true or a false statement? Can somebody answer to this question? Yes, somebody can attempt to answer to this question. Shashi Kumar, Manisha. Okay. Yes, this is a true statement actually. So this is the ASTM G109 test that is being talked about. So basically what is done is that NaCl solution. So let's say this is a concrete element. There are several rebars, and this is a top rebar. It's a top rebar, and these are the bottom rebars. And the sodium chloride solution is poured over the surface, and there's an electrode is connected to this bottom rebars. So what essentially is occurring is that you're exposing the top rebar to chlorides, and that will, so this top rebar will act as an anode since it is exposed directly to the chlorides, and it will start to corrode. While the bottom rebars, the potential or the current is measured in the bottom rebars, and this will act as cathodes. So the bottom rebars are act as cathodes, and the top rebars act as anodes. And this is known as the macrocell corrosion. So macrocell corrosion is basically when different rebars inside the concrete element, they act as anodes and cathodes. So in this case as well, the top rebar is acting as an anode, while the bottom rebar is acting as cathodes, and this is known as a macrocell corrosion. What is a microcell corrosion? In the case of microcell corrosion, this in the same surface of the rebar, let's say in the same surface of the rebar, there's a pitting kind of a corrosion, and this pit acts as a node, while the surface of the rebar acts as a cathode. So on the same rebar, the corrosion is occurring with the cathode being the surface of the rebar, while the pit being the anode of the rebar. This is the microcell corrosion. And in this case, the ASTM G109 standard, in this test, what they do is this measures the current between the substrate concrete that is present between the anodes and cathode. So this is, let's say, this is the current. So this test measures this current between the surface of the concrete between the anodes and cathodes, while it doesn't measure the current going on at the anode location on the top rebar surface. So this is only, let's say this is the 1 and this is the 2 current. This measures only the current 1. And hence it only gives us an idea about the macrocell corrosion. This is what is mentioned. This only gives an idea about the macrocell corrosion that is occurring. So, in case of highly resistive concrete systems, as we mentioned, like whenever we are using supplementary cementitious materials like, let's say, fly ash or silica fume, metacolin, anything, any supplementary cementitious finer material, they tend to refine the pore structure. They tend to refine the microstructure of the concrete, and the microstructure becomes very compact. So it has a less permeability, less connected pores, and therefore uh, the current, the macrocell corrosion cannot occur because this current, they have a very high resistivity. The concrete has a very high resistivity, and therefore it will not allow for the current to pass. And therefore, in this case, when the test is measuring this current number 1, it will show very low current values because the concrete, the substrate concrete, has a very high resistivity. So even if there is corrosion occurring at the anode location, there is a microcell corrosion at the anode location. This is the microcell current, and this is the macrocell current. So even if there is a microcell corrosion occurring at the anode location or the top rebars due to the application of the chloride, it will not indicate any kind of a corrosion. This test will not give us any corrosion of the microcell that is occurring at the top rebar. It will only give us the macrocell corrosion. And in the case of these highly resistive concretes, yeah, since the resistivity of the concrete itself is very high, therefore this test will give us very low values of corrosion, even if there's a corrosion occurring at the steel reinforcement, which is exposed to the chlorides, the microcell corrosion. So this is true. This test is only valid for concretes that have a high permeability or a very low resistivity values, uh, and this is not applicable to concretes which are very highly resistive systems, which are basically which have SCMs or supplementary cementitious materials and have very refined pore structure. So this is a true statement. Moving on to the fourth question. A bridge is located across a river in the coastal region of Mumbai. The following are the available data from the tests conducted on the bridge. Which of the available data would be required to estimate the corrosion initiation time? And the given data are the surface resistivity of concrete, the chloride diffusion coefficient of concrete cover, aging factor, surface chloride concentration, chloride threshold of the steel concrete system, half cell potential of the steel rebar. Which of these options would you choose and why? Yes, somebody would like to answer.
Sir,
Yes, sir.
sir, sir, it is the chloride diffusion coefficient, sir. Sir. The main
Okay.
reason for corrosion is the reduction of the pH value of the concrete.
Okay.
Whenever it will product the steel reinforcement like passive layer,
Mm-hmm.
whenever the pH value is more than 9 or 10,
Right.
but this passive layer is destroyed by the chloride and the carbon dioxide.
Uh-huh.
Whenever the pH value is reducing, then the corrosion will start initiating. So
Okay.
hence
Right.
the chloride resistivity penetration, this the one of the answers, sir. Chloride
Okay.
diffusion coefficient, and the aging factor also is one of the reason,
Mm-hmm.
because the
Is
carbon dioxide react with the concrete, it will reduce the pH value of the concrete.
okay.
So the aging factor also one of the important factor.
How does the aging factor affect? What is the aging factor? Can you tell me? All right. Any other options that you want to choose?
The surface chloride concentration, because it is located in the seashore area, sir, coastal region. The
Right.
chloride is one of the main reason for corrosion, sir.
Right. Good.
So the how much it is surface chloride concentration also very much essential, sir, because
Uh-huh.
the chloride and the carbon dioxide, these are the main reason for reduction of the pH value of the concrete. This chloride already it is in acidic in nature. It
Right.
may be in like water also is there chloride, and also some of the admixture also may contain chloride. So this surface chloride concentration is very important factor to find out the life of the initial propagation of the corrosion, sir.
Right.
So it may be the reason this chloride threshold also may be answer, sir. This.
Okay. Okay. And half cell potential and surface resistivity, why would you not choose them?
So this is they asked the initial time, sir. Initial factor this will come, sir.
Okay. Okay. Fine. Thank you.
Okay. Thanks.
Okay, thank you, Sashi, for answering this question. Yes, these four are options are the data that will consider to assess the corrosion initiation time. So first of all, we'll go discuss one by one. What is the surface resistivity of concrete? We have discussed it in the last session as well. So uh, there's this Venner probe which has four electrodes, and it is placed over a concrete surface, and it measures the resistivity between the two. So so the concrete surface has to be saturated first, and it measures the resistivity. So whenever the probe is rolled over the concrete surface, it measures the resistivity between these two internal electrodes, right? And it will only give you an indication of the resistivity of the surface concrete. Since it is a surface resistivity technique, it will only give you an idea about the resistivity of the surface concrete, and that is the concrete cover, and not the substrate or the core of the concrete. It will not give you an idea about the core of the concrete, first of all. Second, the for this test to be carried out, the concrete has to be in a saturated condition, because otherwise the if the concrete surface is dry, so there will be not enough current that will be visible, and therefore it will give very high resistivity values. So for accurate estimation of the resistivity of the concrete surface has to be saturated, and therefore the saturation of the um, uh, on-site elements, that is the structural element that is already present in a structure, so in a building or a bridge deck or any other structure for that matter, the saturation of these elements is not controlled by any engineer. It is already present on site, and therefore the saturation varies with the diurnal variations, the temperature variations throughout the day, and the available moisture conditions. And therefore carrying out the surface resistivity technique is can give you very different results on the same element carried out by different engineers, and it depends on the amount of saturation that you have provided during the test. So it is a relative, it will give you only relative estimation of the resistivity of the concrete and not an absolute estimation. So this is not a good technique to go with. Secondly, we've also seen that whenever there is this problem that whenever the concrete has supplementary cementitious materials, the surface resistivity is going to give you very high values, and therefore distinguishing the different resistivity values of the concrete elements is not that is very challenging for this kind of concrete structures. So the surface resistivity technique is not applicable to estimate the corrosion initiation time. Second is the chloride diffusion coefficient of the concrete cover, and already as Sashikumar has also mentioned that this structure, this bridge is located in a coastal region of Mumbai, and since it is a coastal region, it is going to be exposed to airborne chlorides, and if since this is a bridge, so it is going to be in contact with the sea water as well, which will give you directly splash of the chloride. So as we have also seen in the lectures as well, there is splash of the water. From that, the chlorides can get inside the concrete. Some of the concrete elements like the PS are submerged within the water, and therefore there is a constant saturation, and the water can freely get inside the concrete surface and carry chloride ions along with it. Also, the bridge deck, which is not even submerged in the water, that can be exposed to airborne chlorides, some of the chloride ions can be carried with the water vapors that are rising from the surface of the water body around the bridge, and that they can accumulate over the concrete surface, and they can get inside whenever sufficient relative humidity is available on the concrete surface. So there is sufficient amount of chloride exposure on this concrete bridge because of the presence at the coastal region of Mumbai, and therefore the estimation of the chloride diffusion coefficient of concrete cover is of prime importance to estimate the corrosion initiation time, because the diffusion coefficient of chlorides is what controls the accumulation of chlorides at the rebar site. So as we have also discussed that, and we'll be discussing this again when we're discussing the chloride threshold of the steel concrete system. So the mere presence of chlorides at the concrete surface or inside the concrete will not affect the will not allow for corrosion to occur on the steel surface. There is a chloride threshold value of the steel concrete system. So the different types of steels have, like stainless steels have a high chloride threshold, and therefore they can allow for larger accumulation of chlorides before they start corroding. Again, the different types of concretes, let's say, again we are coming to discuss about the SCMs. Whenever we are incorporating different supplementary cementitious materials in your concrete, the chloride threshold is increased, and therefore larger amount of chlorides can ingress inside the concrete, can get inside the concrete and accumulate before it breaks the passivating film of the steel and the corrosion starts to occur. So this is what is the chloride threshold. So the chloride diffusion coefficient will also give you the time. The chloride diffusion coefficient is dependent on the permeability of the structure, like the pore connectivity and the porosity of the structure of the concrete the concrete microstructure. And so this chloride diffusion coefficient governs the time of the initiation of the corrosion. Basically, the diffusion coefficient is the rate of the ingress of the chloride inside the concrete. So lesser is the diffusion coefficient, longer will be the time of the initiation of the corrosion, and therefore estimation of this chloride diffusion coefficient will give you an idea about the corrosion initiation time. Secondly, aging factor, and as also Sashi Kumar has mentioned, so aging factor is exactly not related to the pH of the concrete, but aging factor is the aging of the concrete. So whenever we are preparing a concrete, you have placed the concrete and the hydration reactions start to occur inside. At that point of the concrete is very porous in nature, because there is less volume of hydration products and there is more water, and if sufficient curing is not provided, this water can dry out and there will be a lot of voids present within the concrete. With the with the passage of time and with the aging of the concrete, the clinker starts to hydrate, and it forms sufficient amount of the hydration products which clog these pores, or which fill these pores, which fill these voids, and hence they refine the microstructure. This is known as the refinement of the microstructure, or the pore structure refinement. The pores are bigger in size in the early ages of the concrete placement, and with increase in age of the concrete, the pores start to reduce in size till a limit. I mean, there will be, it cannot happen that at certain age the concrete will not have any pores left. Pores will still be present, but the size of the pores and the pore connectivity, the total pore volume will reduce with the aging of the concrete. This is known as the aging factor, and this also affects the chloride diffusion coefficients. Let's say at the early age, if the concrete is exposed to a lot of chlorides, and since this is a bridge that is present near the coastal region, this might so happen that just after the placement, uh, since there is the sea, I mean, it's near this, let's say, assuming that it is near the seashore or it is exposed to the seawater, so sufficient chlorides will be available at that location. And just after the placement, the concrete has a very high pore volume, and the chlorides can get inside the concrete, and that will create corrosion, that will allow for corrosion to occur, and that will lessen the corrosion initiation time, or it will lessen the chloride threshold of the steel concrete system. So aging factor has a lot to do with the corrosion initiation time as well, and therefore the concrete that we're choosing to cast in this kind of conditions, this kind of exposure conditions, should be such that it should have sufficient ability to grow a very less porous microstructure at a very early age, right? So that even if at early age it is exposed to chlorides, it will have a very less connectivity of the pores, and the pore volume will be less, and therefore the diffusion rate of the chlorides will be less. So aging factor is also an important element to consider for the corrosion initiation time. The fourth was surface chloride concentration. Again, it will be high since it is a coastal region. Surface chloride concentration will be high, and it again has depends on the concrete. If the concrete is porous, then it will allow for the surface chlorides to get inside. But if the concrete doesn't allow, if the concrete has a compact microstructure, if it doesn't allow the chloride to ingress, then uh, the corrosion will not occur as soon as in the other case, right? So the surface chloride concentration is also important to estimate the corrosion initiation time. And the fifth, as we have already discussed, is the chloride threshold of the steel concrete system. It doesn't only depend on the steel, it doesn't only depend on the concrete, it is a so it is a dynamic relationship, or a synergistic relationship between the steel and the concrete system, which gives rise to this chloride threshold of the total concrete element. So these four values are of importance to estimate the corrosion initiation time. Again, half cell potential of the steel bar, we have already discussed that it only gives us the relative values of the probability of corrosion and not the absolute values. And again, it comes with the problem of the saturation of the concrete element before carrying out the test, right? And it'll give you an rough idea of the contours, or the possible locations where corrosion might occur, but it will not give you an estimation of the corrosion initiation time. This will only be applicable after the corrosion has started. So then only you'll be getting high voltage values in case of half cell potential, but you won't be getting any absolute idea of the corrosion initiation time from the half cell potential values. So these four are the correct options, and this is a typical uh, degree of corrosion, or the rate of propagation of or the different phases of the corrosion that occurs inside a steel reinforcement in the concrete. So till the corrosion initiation, there is no corrosion occurring. So this is a corrosion free initiation phase, as we call it. At this point, so in case of a chloride induced corrosion, this is the chloride threshold as well. Once the chloride threshold is reached and the passivating film is broken, Then this is the corrosion initiation phase, and beyond this, the corrosion starts to propagate. And so once this corrosion starts to propagate, it will cause expansive stresses within the concrete, and the concrete will start to crack. And at a certain maximum damage level, we have to decide that this concrete element needs repair, and hence we cannot allow any further damage, because that will cause the failure of the concrete structure, right? So these are the different phases of the corrosion. All right. Moving on to the fifth question, and this is the correct answer of this question. Yes. Moving on to the fifth question, spalling of cover concrete was observed on the side faces of columns of an overpass. Side faces of columns of an overpass. Among the choices, what are the two best performance requirements to be considered for selecting a suitable material for near surface patch repair? So you have to carry out a patch repair on a concrete columns on a concrete column of an overpass. So overpass is basically a um, over bridge kind of a structure that is passing over the road. There is a road or a highway that is going on. So there's a pavement beneath, and there's an overpass. Let's say it's a pedestrian overpass or something, which allows for the pedestrians to cross from one side to the other side of the road. So there are these columns on the sides of the overpass, and they have spalling of the cover concrete, and you have to carry out a near surface patch repair. And which of these two uh, performance requirements that you would select for this kind of a repair, and why? Can you somebody answer to this question? All right, let's go one by one. The first one is the high flexural bond strength with the substrate. Now, this flexural bond strength, high flexural bond strength of the repair material is required when you're applying the repair material on a concrete surface that is expected to sag. Let's say it's a beam element, right? It's a beam element, and the bottom surface of the beam element needs a repair, patch repair, right? So you have to do kind of the patch repair from the bottom of the beam reinforcement. So in case of flexural element like the beam or a slab element, whenever you're carrying out this patch repair at the bottom surface, this patch repair material is expected to sag if it is not provided with a sufficient support from the bottom. And at that in that case, you'll need for the patch repair material to be such that it will have a high flexural bond strength with the substrate concrete. This is the substrate, and this is the repair material, right? So it needs to have a high flexural bond strength when it is carried out this patch repair is carried out on a surface which is expected to sag. But in case of columns, since the columns are compression elements, a high flexural bond strength is of no use, because the concrete element is going to carry the compressive loads, and therefore there is no flexural load applicable on the concrete, and therefore the flexural bond strength need not be high for the repair material, right? So this is not the option. Again, high tensile strength. Since this is again the same answer is applicable, since it is only a compression element, you need not have a high tensile strength, because uh, there is no application of the tensile loads on this concrete element, and therefore there is no need for a high tensile strength of the repair material. But a high shrinkage resistance is required. High shrinkage resistance, why? Because whenever you're applying this repair material on the substrate concrete, if the repair material has a high shrinkage, high degree of shrinkage, then it will cause cracking of the repair material itself, as well as sometimes it will induce cracking in the substrate concrete that is present, um, already present in the element. So whenever these repair materials are applied on the concrete surfaces, if these repair materials tend to shrink, then there is debonding of the repair material. If this shrinks, there is debonding of the repair material from the substrate concrete, and it defeats the purpose of the repair. So you spend a lot of money doing this repair and maintenance work, and if the repair material itself has a high degree of shrinkage, then it'll chip off, or it'll debond or delaminate from the concrete surface, and it'll, so I mean, in fact, it'll allow more transport of the ions and water inside the concrete. So that will create a lot of problems. So therefore the repair material needs to have a high shrinkage resistance. Again, the last option was high shear bond strength with the substrate, and this is typically very useful in the case of concrete columns, or in any case, in the case of beam elements as well. Whenever you're applying this repair material on the concrete columns, and there is this compressive loads, there is this vertical loads coming to this vertical elements. If there's a there is the repair material doesn't possess a high shear bond strength, then there will be shear cracking induced between the repair at the interface of the repair material and the substrate concrete. So the, let's say, the substrate concrete will be able to take this shear loads, since the interface between the repair and the substrate concrete will be a weak section, and therefore the repair material might tend to uh, will not be able to take the shear loads, while the substrate concrete will be able to take the shear loads, and therefore there might be a cracking caused bit at the surface of the interface of the repair material and the substrate concrete, and therefore to avoid this kind of a cracking, the shear bond strength of the repair material with that of the substrate concrete needs to be high, and therefore these two answers are correct. The shrinkage resistance needs to be high, and the shear bond strength of the repair material with the substrate needs to be high. Moving on to the sixth question. Just give me a moment. Yes. Uh, Confinement using fiber reinforced polymer laminates, FRP laminates, is selected as a repair strategy to strengthen the girders of a bridge. Select the appropriate properties given in the list below to be included in the tender document. So an FRP laminate system is being chosen as a repair strategy for the girders of a bridge. And what are the properties? What are the different performance the performance properties that you would like to choose for the repair FRP laminates to have, and you have to include that in the tender document. And these properties listed are highly elastomeric in nature, high elastic modulus, high UV resistance, anti-corrosive, high compressive strength, highly permeable. Which of these properties would you choose in the FRP laminates for the repair? Let's go one by one. Highly elastomeric, and this term itself, elastomeric, is ambiguous. Anything, any material has, so any real solid that is present on the Earth's surface is viscoelastic in nature, meaning that it'll undergo creep under certain loads, sustained loads, and it will undergo an elastic deformation until the elastic limit of the material when an instantaneous load is applied, until elastic limit, right? So there is a certain degree of elasticity of any material, every material. So just mentioning that highly elastomeric in nature is an ambiguous term, and therefore it should not be included in the tender document. The second is the high elastic modulus, and this is elastic modulus is a technical term. So mentioning only elastomeric doesn't serve the purpose. Rather, you should mention that it needs to have a high elastic modulus, and elastic modulus is the ratio of the stress versus strain of the, so let's say this is the stress strain curve of a certain material, and it is the elastic modulus is defined as the ratio of the stress to the strain of the material within the elastic limit. Right? So a material needs to have a high elastic modulus, and this is typically required because these are the girders of a bridge, and since the girders of a uh, bridge are flexural members, and they need to have a high elastic modulus so that it will restrict the deformation of the base, the deflection of the girders, and therefore it will serve the purpose of the repair material. So these fiber reinforced laminates need to have a high elastic modulus, and this should be the chosen property. High UV resistance, yes, we've also seen that in the previous lectures as well. These FRP, the fiber reinforced polymer laminate, have a tendency of degrading when they are exposed to the ultraviolet rays of the sunlight. So what happens essentially is that whenever you applied this FRP laminates, you have wrapped up the girders of the bridge with these FRP laminates due to the exposure to the sunlight and the UV rays coming from the sunlight. These laminates get debonded from the concrete surface. They tend to degrade. They become brittle in nature. There is cracking over the laminates, the FRP laminates, and they debond from the concrete surface, and thereby defeating the purpose of the repair. So whenever choosing the material for the repair, and you need to mention in the tender document that the FRP laminates need to have a high UV resistance. Again, the third is anti-corrosive in nature. Yes, the repair materials, the any repair material for that matter, if you're ensuring, if you need to ensure a long-term durability of the repair or the maintenance work that you have carried out, then the repair material needs to be anti-corrosive so that it will not corrode itself, neither will it allow for the corrosion to occur inside the concrete, and therefore it needs to be anti-corrosive in nature. So these three are the right answers. Again, high compressive strength is not chosen because just mentioning a high compressive strength is of no use. For any repair material, before choosing a repair material, it needs to, if the substrate concrete, the compressive strength of the substrate concrete needs to be evaluated first, and then only the repair material should be chosen such that the repair material will have a compressive strength that is similar or comparable to that of the substrate concrete. Otherwise, there will be differential settlement because the load carrying capacity of the repair material and the substrate concrete is different, and therefore there will be differential settlement within the structure that will create cracking of the concrete structure. So that is not that is an unwanted kind of a failure in the case of this concrete durability issues, and therefore we can't decide only the high compressive strength based uh, of the repair material without determining the compressive strength of the concrete element that is already present. First, secondly, since these are only FRP laminates and they only serve the purpose of, so when they are wrapped around the bridge girders, they only serve the purpose of restricting the deformation or the deflection of the bridge girders, the beam elements that are present beneath the bridge. So they restrict the deformation, they restrict the amount of deflection of the girders, and they have a very high tension capacity. So the tensile strength of these FRP laminates should be very, very high, should be very, very high. And there is no need for a high compressive strength. This will only, including this in the tender document, will only increase the cost of the repair and will not serve any purpose for the repair, right? So these three are the correct answers. Question number 7 was an expansion joint with severe cracks located on a highway bridge is shown in the photograph. What would you consider to enhance the crack resistance of concrete in such cases? So this is the expansion joint, and these are cracks around the expansion joints. And the cases listed out are increased compressive strength alone, enhance toughness and fatigue life by incorporating fibers in the concrete, use concrete with low shrinkage resistance, ensure that the expansion joint is free of foreign materials such as sand, dirt, soil, and even powdered concrete asphalt materials, provide steel sections to form the boundary of concrete slabs at the joint region. Which of these options would you choose to enhance the crack resistance of the concrete at this location? All right. Increasing the compressive strength alone will not serve the purpose of reducing the cracking. So this is not the answer, because just increasing the compressive strength, of course, increasing the compressive strength will increase the abrasion resistance, and since it is a highway bridge, so there is a lot of chance of abrasion at these expansion joints due to impact loads and due to the moving of heavy vehicles and the friction between the tires of the vehicles and the concrete surface. That will accelerate the abrasion process, and um, having a higher compressive strength will increase the abrasion resistance. But only that will not serve the purpose of reducing the cracking in this concrete element. Second was enhance toughness and fatigue life by incorporating fibers in the concrete. This is a good choice because whenever you're incorporating fibers inside the concrete, what these fibers do is that whenever there is cracking of the concrete surface or the concrete element, these fibers tend to bridge the cracks. So this is known as the bridging effect of the fibers. So they tend to bridge the cracks, and hence they restrict the propagation of the cracks. So the crack width is less, and so whenever the concrete element is stressed due to, let's say, shrinkage cracking, shrinkage, or like different types of shrinkage, plastic or autogenous shrinkage, or drying shrinkage, or thermal shrinkage, any kinds of loads that is applied on the concrete surface. So these fibers, they tend to align perpendicular to the direction of the crack propagation, and therefore they restrict the crack width. and hence several micro cracks instead of large cracks. Several micro cracks are incorporated within the concrete, and the concrete element has a higher ductility overall. So this will enhance the toughness and the fatigue life of the concrete, and therefore it will reduce the cracking that is shown in the figure. So and incorporating fibers in the concrete will enhance the toughness and fatigue life of the concrete. And this is a true statement. The third was use concrete with low shrinkage resistance. And since we are experiences at these locations when at this, so this is the location of the expansion joint or the joint between two concrete slabs or two concreting processes. So at these locations, there is a high chance of occurrence of shrinkage cracks, and we need to have a concrete with a high shrinkage resistance, and therefore this is a wrong statement. The fourth was ensure that the expansion joint is free from foreign materials such as sand, dirt, soil, and even powdered concrete asphalt materials. And this is true because if this expansion joint is filled, sometimes it gets filled because of the winds or the erosion and the transport of the sand and dirt by the movement of the vehicles as well. So these sand and dirt tend to accumulate on these expansion joints, and whenever the purpose of this providing this expansion joint is that whenever there is temperature stresses, there is increase in the temperature and the concrete elements tend to uh, expand in size. This expansion joints will allow for the concretes to expand, and I mean there will be this provides an allowance for the dimensional changes within the concrete structure, right? And if these expansion joints are accumulated by the sand and dirt, then it will again restrict the dimensional change, and that will cause cracking in the concrete. So the purpose of providing this uh, expansion joints will not be served, and therefore this these expansion joints need to be free from the sand, dirt, or any powdered material. Right, so this is a correct statement. Just give me a moment. Yes, and the last option was provide steel sections to form the boundary of the concrete slabs at the joint region, and this typically helps because um, these expansion joints are prone to impact loading from the concrete, the movement of the vehicles, and providing these steel sections will, since steel has a higher toughness and it is ductile in nature, and therefore it will be able to sustain the impact loads that is coming from the movement of the vehicles, and therefore providing these steel sections will also decrease the increase the crack resistance of the concrete caused due to the abrasion or the impact loads coming from the travel of the vehicles. So these three are the correct options. Right? Moving on to the last question, and this is a good question. It is very important to ensure that the repair material selected is compatible with the substrate material in any repair work. The graphs shown in the column 1, I've shown the graphs in the next slide. In the column 1 represent the stress strain behavior of substrate and repair materials. In the schematics given in column 2, the bulging indicate elastic deformation. The cracks indicate occurrence of plastic deformations. I'll highlight these. The bulging indicate elastic deformation. The cracks indicate occurrence of plastic deformation. And fracture or failure. And the vertical arrows indicate the applied load. And the thick horizontal plates provided are very stiff. S and R are the indicate the substrate material and repair material respectively. Assume that load is released or removed when one of the materials is cracked or fractured. Match one with column 2. Match column 1 with column 2. And in this, this is the column 1 and the column 2. In the first case, in the column 1, it is shown that the stress strain behavior of both the substrate material and the repair material is similar. In the option B, it is shown that in the case B, it is shown that the repair material lies in the elastic region, while the substrate material has gone to the plastic deformation range. And in the option C, it is otherwise. It is vice. It is just opposite of the option B. The repair material has gone to the plastic deformation range, while the substrate material still resides in the elastic range. And in the column 2, it has been shown that the repair material has cracked, while the substrate concrete has not. I mean, it is unaffected. In the case 2, it is shown that both the repair material and the substrate concrete have undergone elastic deformation and in equal amounts. In this third, it is shown that the repair material has gone the plastic deformation, while the substrate material has gone elastic deformation. And in the last case, it is shown that the substrate material has undergone a plastic deformation, while the repair material has undergone elastic deformation. Yeah. Can somebody answer to this question? All right. Yes, matching the first one, the column 1A option, since the repair material and the substrate material both have the similar stress strain behavior, and therefore this will match with the option 2 of the column 2, which have the similar bulging. Both are within this elastic range. They have the similar bulging patterns, and the deformation in both the repair and the substrate material is similar. And therefore, this matches with the option A of column 1. So A matches with 2. Coming to B, the repair material is in the elastic range, but the substrate material has gone to the plastic deformation range. Plastic deformation is basically when without a further increase in the stress, the strain goes on increasing, right? And therefore, so we can see that in the case 4, the substrate material has undergone cracking and plastic deformation, while the repair material is still in the elastic range, and therefore option B matches with option 4 of the column 2, and it is just the opposite in case of C. C matches with, okay, There is some okay, sorry. Yes, option B actually matches with the option 3 from the column 2. In this case, uh, I guess the answers given are not okay. The given answers are not actually correct. The correct answer is going to be this option. So the option B matches with the 4 because the repair material is in the elastic range and the substrate material has undergone cracking and plastic deformation. In this, and the C option will match with 3. The substrate material is in the elastic range and undergone bulging, while the repair material has undergone cracking and is in the plastic range. And hence the correct answer will be A matches with 2, B matches with 4, and C matches with 3. This is the correct answer. I guess the correct answer given in the answers of the NPTEL course was A2, B3, and C4. But A, since although A is matches with 2, but B and 3, B doesn't match with 3 and C doesn't match with 4, the correct answer is going to be A matches with 2, B matches with 4, and C matches with 3. This is the correct answer. All right. So that ends the assignment 5. There are only 8 questions. Thank you for attending this session. And if you have any questions or any doubts related to this session or the week 5's lectures, then you can go ahead and ask. This session will go on till 1 p.m. And if you have any questions, you can raise your hands or you can, I've unmuted your mics, so you can ask. Otherwise, you're free to leave. All right, we are closing this session for today. We'll meet again on the next Saturday from 6 to 8 p.m. Thank you.